Hello everyone, I am Honar Gupta, a PhD scholar at IIT Kanpur. Today I will talk about some problem related to week 5 of the course Fundamental of Supersonic and Hypersonic Flow. If you have any doubts, you can post it in the Google forum of the group, and you can ask the question directly also. So this first problem is related to perfect gas equation of the gas. If the product N K, where N is the number density and K is the Boltzmann constant, N is the number density this is number of particles per unit volume. and K is the Boltzmann constant of a gas. And this product has a value of 320 joule per meter cube Kelvin. The molecular weight of the gas is 32 kg per kilomole, and its density is, we have to find its density. Here R equal to 8314 joule per kilomole Kelvin. This is the universal gas constant. So we have to find this value. So first we will see some different forms of perfect gas equation. Perfect gas is a gas in which intermolecular forces are neglected. So in perfect gas we neglect the intermolecular force, and we also neglect the volume of the particles of the gas, and it is given by PV equal to mRT, where P is the pressure of gas, V is the volume of the gas, M is the mass of the gas, T is the temperature of the gas, and R is the specific gas constant. It is different for each and every gas, and it is given by R bar upon M. This M is here also I will use bar. For the molar quantity I will use bar. So this R bar is universal gas constant, and this M bar is molecular weight. And the value of R bar is constant for each and every gas. It is given by 8314 joule per kilomole Kelvin for all gases. It was given before also. R equal to 8314 joule per kilomole Kelvin. And R for air is given by 287 joule per kg Kelvin. It is different for each and every gas. Now we will see different forms of partial gas, perfect gas equation. One is P V equal to RT. Here see that this P is small, and this V is nothing but specific volume, which is volume per unit mass. So we have this equation before, PV equal to mRT. If we divide M on the both sides, then it will become PV upon M equal to RT. M is mass, and V upon M, volume per unit mass, is what? Specific volume. So it will give PV equal to RT. Other form is P equal to rho RT. So, and rho is density. So we have this form PV equal to RT before. If we divide both sides by small v, specific volume, then we will get P equal to 1 by V RT, which is equal to rho RT. Rho is nothing but 1 by V. If you see definition also, V is volume per unit mass. So its reciprocal will be mass per unit volume. So this way we get the equation P equal to rho RT. Now we will see third form, PV equal to nRT. Here this R is different. So we will use R bar here for differentiating here. This R bar is nothing but universal gas constant. Universal gas constant. And this N is number of moles. We have one formula before, PV equal to mRT. First one which we saw before. Now we will divide by molecular weight and multiply by molecular weight on both sides. So on for right hand side. So this M, mass upon molecular weight, will become number of moles. Mole, definition of mole is nothing but mass upon molecular weight, mass. And we have seen that before, this R bar is universal gas constant is given by R upon M bar, is molecular weight. So we will get molecular weight into, specific gas constant is given by R bar upon M bar. R bar is universal gas constant, M bar is molecular weight. So by multiplying these two, we will get R bar. Another form we will see P V equal to RT. This V is different. This V is given by molar volume. Here also, for all molar quantity, I am using this bar on top of it so that you can differentiate. So we have this form, and also PV equal to nRT. So we will divide both sides by n, number of moles. So what we will get, molar volume is what? Volume upon number of moles. So volume upon number of moles is what? Molar volume. So we will get PV equal to RT. One form is related to concentration. Here C is the concentration, P equal to CRT. C is the concentration, which is mole per unit volume. Number of moles per unit volume. So we have this form PV equal to N bar R bar T, and if you divide both sides by volume, then you will get P equal to N bar upon V into R bar T. N bar upon V is what? Number of moles per unit volume, which is nothing but concentration. So we will get CRT. Another form is PV equal to eta RT. And here eta is mole mass ratio, which means number of moles per unit mass. So we have this form PV equal to nRT, N bar R bar T. So we will divide both sides by M, mass of the gas. So we will get this V by M is nothing but a specific volume, and N bar upon M is number of moles per unit mass, which is nothing but eta. So we will get PV equal to eta RT. All these forms which we have seen till now are generally in terms of mass or mole. Now we will see in terms of number of particles. This is the form PV equal to capital N KT, where N is the number of particles and K is the Boltzmann constant. We have this form PV equal to nRT, this form. Here we will multiply and divide right hand side by Na. N is nothing but Avogadro number, Avogadro constant. Na is 6.022 into 10 to the power 23. This is its value. It is nothing but number of particles in 1 mole of gas. So N is number of particles in per mole, 1 mole of gas, and this is the number of mole. So this N will give total number of particles. Similarly, if we divide this R bar by Na, we will get another constant, which is K, which is called Boltzmann constant. So we will get it given as PV equal to NKT. Now if we divide that volume on both sides, then we will get another form, P equal to small nkt, where n is the number of particles per unit volume, which is also called number density. We have seen in the question before. So we have this equation PV equal to capital N KT. So if we divide by volume on both sides, then we will get this N, capital N upon V KT. N is the number of particles and V is the volume. So we will get P equal to small n KT. And this N is the number density here and K is the Boltzmann constant. The value of this Boltzmann constant is 1.38 into 10 to the power minus 23 joule per Kelvin. So these are the all form written together. Equation of state. EOS is the equation of state. So there are three types of form. One is the mass basis, where we are using a specific gas constant. Another is the mole basis, where we use the universal gas constant. And another is the particle basis, where we use the Boltzmann constant. So in the mass basis, there are three equations. PV equal to mRT. In the first form which we saw, P, here in the equation everywhere P is the pressure. Here P is pressure. And T is the temperature. And R, I already told, this is the specific gas constant, capital I is the universal gas constant, K is the Boltzmann constant. Here M is the mass of the gas and capital B is the volume of the gas. The second form, P small b equal to RT, where V is the specific volume, which means volume per unit mass. Third form, P equal to rho RT, where rho is the density. In the mole basis, we have four equations. PV equal to nRT, where this N is mole, number of moles. I will keep the bar here for all the molar quantity. Second form is P V bar equal to R bar T, where V bar is molar volume, volume of 1 mole of the gas. Another is P equal to C R bar T, where C is the concentration, number of moles per unit volume. PV equal to eta RT, where eta is the mole mass ratio, number of moles per unit mass. Particle basis, we have two equations. PV equal to nkt, where capital N is number of particles, and P equal to small nkt, where small is the number density, number of particles per unit volume. Now we will solve the problem. So in the problem was that we have product of Nk, which has value of 320 joule per meter cube Kelvin, and molecular weight of the gas is 32 kg per kilomole, and density, we have to find its density. Here R is given by 8314 per joule per kilomole Kelvin. So we have the Nk value, it is 320 joule per Kelvin. joule per meter cube Kelvin. We have molecular weight, which is 32 kg per kilomole. So we are going to P equal to NKT. And this is also equal to rho R T. We have to find rho, that's why we are using this form, and we know the value of NP, that's why we are using this form. This T will cancel out, so we get rho equal to NK upon R. But one thing to notice, this R is a specific gas constant, we don't know its value. So we will write this R in the form of universal gas constant, which is R bar upon N bar. Now we will put its value. Nk is 320. We will write the unit also, joule per meter cube Kelvin, into m bar is 32 and R bar is 32 kg per kilomole. And R bar is 8314. So I was solving one problem related to perfect gas equation. The problem was that if the product of Nk, where N is the number density and K is the Boltzmann constant of a gas, has a value of 320 joule per meter cube Kelvin, and molecular weight of the gas is 32 kg per kilomole, its density is, we have to find its density, and value of R is given by 8314 joule per kilomole Kelvin. To solve this problem, we are using two forms of ideal gas equation. One is P equal to NKT and one is P equal to rho RT. This P equal to NKT, here N is the number density and K is the Boltzmann constant, and P equal to rho RT, where rho is density and R is the specific gas constant. Nk value is given in the problem 320 joule per meter cube Kelvin, and molecular weight is given as 32 kg per kilomole. As pressure will be the same, so we equate these two parts together. So P equal to NKT equal to rho RT. Here T will cancel. So we will get rho equal to Nk upon R. But we don't know the value of specific gas constant. So we will write this R in terms of universal gas constant and molecular weight. So this R is equal to R bar upon N bar. N bar is molecular weight. So we have substituted here. We got Nk M bar upon R bar. Now we put the value. Nk is 320 joule per meter cube Kelvin. M bar is 32 kilojoule per kilomole, and R bar is 8314 joule per kilomole Kelvin. If we put this value in the calculator, we will get 1.2317, and unit also we can say check, this kilomole will cancel out, Kelvin will cancel out, joule will also cancel out. We will get kg per meter cube. This is density. And in the option, there was one option B, which is 1.23 kg per meter cube. This is the answer. Is there any doubt in the question? If there is no doubt, I will move to the second question. Gives free energy per mole of a gas mixture is given by. There are four options: H by T plus S, HT minus S, Ts plus H, H minus Ts. Here H is the enthalpy, T is the temperature, S is the entropy per mole of the mixture respectively. This is nothing but we have to give the definition of gives free energy. How gives free energy is defined. So it is very simple problem. So gives free energy is a thermodynamic state variable, which is given by G equal to H minus Ts. Here G is in the per unit mole of mixture of the gas, and H and S are also given for the per unit mole of the mixture. Here we already know H, T and S all are state variable. So G is also a state variable. So answer for this question will be D. We will see other problem. Molar volume in terms of gives free energy G is given by. So molar volume V. What was this? Volume upon number of moles. We have to find how it is given in terms of gives free energy. So we will write this question generally. If you remember the relation, you can directly get the answer, but we will derive here. So we will first use the definition of gives free energy. G equal to H minus Ts, and H mentioned before also. This all quantity which I will use in the capital letters are given for per mole of the mixture of the gas. Like this gives free energy is also in the per mole of the mixture of gas, enthalpy and entropy also. I will take the derivative. Then dG equal to dH minus dDs minus sdt. I will keep these two terms. I will take these two terms on the left hand side. So I will get dH equal to dG plus TdS plus sdt. From the definition of enthalpy, we know that H equal to U plus P V bar. We have taken molar quantity, so and U is the internal energy per unit mole of the mixture of the gas, and H is also enthalpy for per mole of the mixture of gas, and V bar is molar volume. We will take the derivative. dH equal to du plus pdV bar plus v bar dP. From the first law of thermodynamics, we know that du plus pdV bar is nothing but reversible heat. Del Q reversible. So from this we will get del Q reversible equal to dH minus v bar dP. Entropy can be written as the sum of reversible and irreversible entropy. So dF equal to ds reversible plus ds irreversible. ds reversible is given by, from the definition, del q reversible upon t plus ds irreversible. We can substitute from the equation 2 for del q reversible equal to dh minus v bar dp. We will substitute it here, so we will get ds equal to dh upon t minus v bar upon t dp plus ds irreversible. We will multiply t on both sides, so we will get t ds equal to dh minus v bar dp plus t ds irreversible. Now we will substitute from the equation 1 value of dh. dh was dg plus tds plus sdt. We will substitute it here, so we will get tds equal to dg plus tds plus sdt. This was dh, we substituted it, minus b bar dp plus t ds irreversible. This tds terms will cancel out, so we will get the value of dg equal to, we will take these terms right hand on the left hand side, so we will get dg equal to minus s dt plus b bar dp minus t ds irreversible. We will name it equation number 3. One thing to note that for equilibrium there will be no irreversible entropy. So ds irreversible will be 0, this term will be 0. So we can see that G will depend on only pressure and temperature. This entropy, we know that it is function of pressure and temperature only, and this P bar can also be written as a function of pressure and temperature using the perfect case relation. So ultimately this free energy will be function of pressure and temperature for equilibrium flow. But for chemical non-equilibrium, this ds irreversible will not be 0, and G will depend on Ni. Ni, which is number of particles of species I per mole of the mixture of the gas. Ni is what? One time more, which is number of particles of species I per mole of the mixture of the gas, because it is changing with time. There is chemical non-equilibrium, so this Ni is changing with time, that's why this G will also depend on Ni. So G is the function of P, T and M, N1, N2 till Nn, and here small n is number of species in the mixture. We will take the differentiation. So dg equal to dou g by dou p at constant temperature into dp plus dou g by dou t at constant pressure into dp plus sigma I dou g by dou ni dni. For each ni we are taking a differentiation and adding it. So we have in the simplified form written as a summation. If we compare this equation with the third equation, this one, if you will see that there is in this equation there is one term with dt and one term with dp, and there is third term. In this equation also, if you see, there is one term with dt, one term with dp and one third term, and we have to find the molar volume. So if you see in this equation, this molar volume is this term with the dp. So molar volume V bar can be given by, if we compare the dp term, then we will get V bar equal to dou g by dou p at constant temperature. This is the answer. If you see, option also dou g by dou p at constant temperature. This will be the answer. We'll see another problem. The entropy caused by chemical non-equilibrium is expressed by. We have to find ds irreversible. Entropy caused by chemical non-equilibrium is expressed by. There are four options: minus 1 by T sigma I Gi dni, 1 by T sigma I Pi dgi, 1 by P sigma I Gi dni, 1 by T sigma I Hi dni. If you know the relation, you can directly give its answer. And in this option, Gi is gas free energy for species I. Ni is number of moles of the species. Hi is enthalpy of species I. Pi is the partial pressure of the species. T is the mixture temperature and P is the mixture pressure. So we will also derive relation for this. So first we will go back to what we have done before for the dg. We got two equations. This equation number 3, dg equal to minus s dt plus d by dp minus tds irreversible, and one equation dg equal to dou g by dou p d dp plus dou g by dou t dp dt plus sigma I dou g by dou ni dp. We have written these two equations together. Now if we compare, there is one dt term, there is one dp term and one extra term. So these two terms will be equal. So minus t d s irreversible equal to sigma I dou g by dou ni dni. We will name it as expression 4. Here we have already defined that G is gas free energy per mole of the mixture. Now we will define one more term, Gi dash. This is the gas free energy of species I per particle. This is per particle. So for the species I, it will be Ni Gi dash. For species I, gas free energy for the species I per mole of the mixture is Ni Gi dash, because Ni is nothing but number of particles for the mole of the mixture. And if we add all these together, we will get the gas free energy per mole of the mixture. So G equal to sigma I Ni Gi dash. Now if we take the S derivative with respect to Ni, say that it can be written as the sum of n1 g1 dash plus n2 g2 dash plus nn g1 dash. So if we take its derivative with respect to, let's say, n1, then all these terms will be 0. Similarly, if we take with respect to n2, all the terms will be 0. Similarly, if we take its derivative with respect to ni, then it will give Gi dash. Dou g upon dou ni will be equal to Gi dash. So in this equation, dou g upon dou ni, we can substitute it with Gi dash. So we will get, and we have shifted this t to right hand side, so we will get ds irreversible equal to minus 1 by t sigma Gi dash dni. Now we will multiply and divide this right hand side with n. How is that to number? Na into Gi dash. So before, what was the Gi dash? This free energy of the species I per particle. So if we multiply this with Na per particle, so if we multiply it by Na, what will it give? Per mole. Gas free energy of species I per mole of species I. So it will give free energy of species I per mole of I, and it is given by Gi. And dni upon n is what? This is change in dni is change in number of particles of I upon n. So division will give change in number of moles of I. Number of particles upon n is nothing but mole. So this is not change in number of moles of I. So we can write it as dni bar. Both will substitute here. So we will get ds irreversible equal to minus 1 by 2 sigma gi dni bar. You can see the option. There is only one option, which is A, minus 1 by 2 sigma I gi dni. I have used bar, but here it is definition is same. Number of moles of species I. Here also number of moles of species I. And I bar. We move to another question. For an equilibrium chemical reacting gas mixture comprising of 3 species, namely species 1, species 2, species 3, the change in number of moles of species 3 can be expressed as Gi is free energy of a species I, and dni is change in number of moles of species I. There are 4 options: G1 dn2 plus G2 dn1 upon G1 plus G2, G1 dn1 plus G2 dn2 upon G3, minus G1 dn1 plus G2 dn2 upon G3, minus G1 dn1 plus G2 dn2 upon G1 plus G2. For equilibrium chemical reacting gas mixture. Before we got this one relation, ds irreversible equal to minus 1 by t sigma gi dni. This is for irreversible. Chemical, if there is chemical non-equilibrium is there. So if there is equilibrium, then this term will be 0. So for chemical equilibrium, this ds irreversible will be 0. So if this will be equal to 0, then this summation will be 0. Sigma I, gi, dni will be 0. Now this is for n species. If there are n species in the mixture, so for the C species, it can be written as G1 dn1 plus G2 dn2 plus G3 dn3. We have to find change in number of moles of species 3, which is Gn3. Bar. Here I am using without bar because here also they are given definition without bar. So these two terms we can take the right hand side. So we will get G3 dn3 equal to minus G1 dn1 by G2 dn2, and we divided by G3, then we get dn3 equal to minus G1 dn1 plus G2 dn2 upon G3, which is nothing but option C. Now we will see what is equilibrium constant first, because before solving some question related to this equilibrium constant. So we have derived one equation, ds irreversible equal to minus 1 by t sigma gi dni, and we have also seen for chemical equilibrium this ds irreversible equal to 0, so this term should be 0. Now we will mainly study the equilibrium. We are finding equilibrium constant, so we will go to chemical equilibrium. So that's why sigma gi dni bar equal to 0. We'll name it equation number 5. So our aim is to write this form equation in the different form. Now we have taken a general chemical reaction, which is given by new 1 dash a1 plus new 2 dash a2 plus dot 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 new k dash ak, and it will give the product new k1 dash ak1 plus new k2 dash ak2 plus dot 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 plus new j dash aj. For total species is from 1 to j. Total species are j. Total number of reactant is k. This left hand side are reactants, and total number of product is j minus k. So for our convenience, we will write all the terms on the right hand side. We will take all the terms on the right hand side. So it can be written as sigma I equal to 1 to j nu I ai. So if we take the reactants to the right hand side, their coefficient will become negative, and you can write this as nu I ai equal to 0. Here nu I can have both positive or negative. It can be positive or negative both. It will be positive for products and negative for reactants. For example, we will see one reaction. 2H2 plus O2 will give 2H2. I have not written the condition, like for what condition it will form, what external factor it will form, but we will see this reaction. So for the H2O, what will the mu? It will be 2. This is the 2 for H2O. For O2, if we take it right hand side, it will become negative. So mu for O2 will be minus 1. Similarly, if we take this term right hand side, it will also become negative. So mu for H2 will be minus 2. So we come back to here. So if we see here, any change in number of moles of species I is proportional to mu I. So let's say if we are changing some moles here, let's say we have 1 mole of H2, then how many moles of H2 will form? It will form 1 mole of H2 only. It is proportional to it. And how many O2 will need? 1 by 2 mole of O2 will need to form 1 mole of H2. So we can see that the number of moles of species I is proportional to this stoichiometric coefficient. This coefficient before a reaction is called stoichiometric coefficient. So that is the ratio of this number of moles of species, any change in number of moles of species is proportional to mu I. So in general, for J species, we can write dni bar, ratio dn2 bar, ratio dn3 bar, and so on, dnj bar equal to mu1 ratio mu2 ratio dot 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 muj. Now we will introduce a common proportionality constant. So we will get dn1 bar upon mu1 equal to dn2 bar upon mu2 equal to dash equal to dnj bar upon muj, which is nothing but equal to dj. So we can write dn1 bar equal to mu1 dj, dn2 bar equal to mu2 dj, and so on, dnj bar equal to muj dj. Or we can write dni bar equal to mu I dj. So we are in the equation 5th, we will substitute this dni bar by mu I dj. So we will get sigma I gi mu I dj equal to 0. Now you know that this dj is constant for all species, and this dj can come out. So we will get dgi sigma I gi ni equal to 0. Sorry, gi nu I equal to 0. So this term cannot be 0, so this term will be 0. So sigma nu I gi equal to 0. This is also a condition for equilibrium, chemical equilibrium. So before the heading, you have seen that it is for equilibrium constant. So we are trying to find the equilibrium constant. So now we will take gi equal to hi minus Tfi. What was the gi? Gi was this free energy of species I per mole of I. Here definition I written. This free energy of species I per mole of I is gi. Similarly, enthalpy of species I per mole of I is hi. Entropy of species S per mole of species I is Si. And there is one more relation, Si equal to integration T reference to T Cpi dt by T minus R bar log Pi upon P reference plus Si reference. So if we combine both of these together, then we will get gi equal to hi minus T integration T reference to T Cpi dt upon T minus R bar log Pi upon P reference plus Si reference. If we take pressure as constant and equal to 1 atmosphere, then Pi equal to 1 atmosphere, we will get gi Pi equal to 1 equal to hi minus T integration T reference to T Cpi dt upon T. This Pi will become 1, so for 1 it can be written as minus R bar log 1 minus log P reference. Log 1 is 0 and this minus minus will become plus, so it is nothing but R bar log P reference plus Si reference. So if we compare these two, both equation has this term, and if we write this as this Pi, then it also has this term and this term. Only difference is this term. So this gi can be equal to gi Pi equal to 1 minus R bar T log Pi. And this minus minus will become plus, so it will be plus R bar T log Pi. Now we have the relation before, equation 6. So for equilibrium, this sigma nu I gi equal to 0. So now we will substitute the value of this gi. So we will get sigma integration nu I gi Pi equal to 1 plus nu I R bar T log Pi equal to 0. We will separate these two together, two terms, so it will be sigma nu I gi Pi equal to 1 plus this will also be under sigma nu I r bar t log pi equal to 0. Now you see these two terms r and t. These are constants for each species. So we will take it out of the summation. So our equation will become sigma nu I gi pi equal to 1 plus r bar t sigma I nu I log pi equal to 0. Now see this term. So in this term, it has all the species from I to j, I equal to 1 to j, and what it is doing is it is multiplying the Gibbs energy of species I with its stoichiometric coefficient of both product and reactant. So it is nothing but g equal to 1 for Gibbs energy for pressure equal to 1 for products minus g equal to 1 for reactants. It is nothing but difference of Gibbs energy of products and reactants and at pressure equal to 1. So we'll write it as delta G equal to 1. So we will substitute this delta G equal to 1 and we will divide this equation by r bar t. So we will get this equation delta G equal to 1 upon r bar t, and this term we will put it to right hand side. So we will get minus, I skip one step, but we will get minus sigma I nu I log pi, and we know the log relations. So if there is and log a is nothing but log a to the power n. So we have put in terms of power nu I. Now check this term. Sigma I log pi nu I equal to, we will open the summation. So it will be log e1 u1 plus log e2 u2 plus summation log ej uj. And there is also one relation in the log, that log e plus log e equal to log ab. So these terms are in the form of summation, so they can be multiplied inside of log. So it will equal to log e1 u1 e2 u2 and ej uj. And this multiplication can be written in the simplified form equal to log pi I pi nu I. Pi is nothing but it is used for multiplication. So this is I equal to 1 to j. So we will substitute it in this equation. So we will get this value will be equal to minus delta G be equal to 1 upon r bar t. This log, if we remove this log, we will get pi I pi to the power nu I equal to e to the power minus delta G equal to 1 upon r bar t. And this term is what we called Kp, and this Kp is what? Equilibrium constant. So how do you find this Kp for a reaction? For finding the Kp, we use the Janef thermodynamic tables. Using this table, we can find the value of this Kp. This is the image which I have given for the database. Now we will see one problem. In the dissociation reaction, O2 plus N gives 2O plus N. The change in gift free energy at 1 atm is given below. What we have to find? Change in gift free energy at E equal to 1. So I have told that this change in gift free energy is defined by gift free energy of the product minus gift free energy of the reactant, which is nothing but sigma I mu I gi pi equal to 1. So we will first find what are the stoichiometric coefficient for the each term. Our reaction is O2 plus N gives 2O plus N. So for the first reactant product, we will see mu O equal to 2, mu N is 1. And write it here. These are product. Mu N equal to 1. And for the reactant, mu O2 equal to minus 1. This will go that side, so it will become minus 1. This reactant. And mu N is also, it will go that side, it will become minus 1. So delta G equal to 1 is given by the sigma mu I gi pi equal to 1. We will expand it. So it will contain all the product and reactant. So these two are product and these two are reactant. So it will become mu of GO P equal to 1 plus mu N GM P equal to 1 plus mu O2 GO2 P equal to 1 plus mu N GM P equal to 1. We put all the values. Mu is equal to 2, mu N equal to 1, mu O2 is minus 1 and mu N equal to minus 1. We will put it and we will get it equal to 2 GO P equal to 1 plus 1 GN P equal to 1 minus 1 GO2 P equal to 1 minus 1 GN equal to 1. If you see, these two terms are same, so they will cancel out and we will get 2 GO P equal to 1 minus GO2 P equal to 1. We'll check the option. This one, 2 GO P equal to 1 minus GO2 equal to 1. This is the same, so this will be the answer. Next question. In the law of mass action Kp equal to pi I pi mu I, where pi is partial pressure of the species I and mu I is the stoichiometric mole number of the species I, positive for the product and negative for the reactants. The following statement or statements is or are true. Option A, Kp is the function of T temperature. Kp is the function of both P and T temperature. K is the function of P, T temperature and T time. Kp is defined as equilibrium constant. So this option is, you can straightforward say that we already defined this Kp as equilibrium constant. Now we see on what properties it depends. So this is the formula of Kp. It is given as pi I pi mu I equal to e to the power minus delta G E equal to 1 upon R bar T. So we have seen before that G is a function of pressure and temperature for equilibrium flow. Why equilibrium? Because this equilibrium constant is only given at equilibrium. And we have for G equal to 1, we have made the pressure as constant. So this delta G equal to 1 will be function of T only. And this term also is function of only T. So this whole term will be function of T only. So this Kp is function of T, temperature only. So this option is also correct. We'll see the next problem. In the dissociation reaction, 1/2 O2 gives O. The equilibrium constant is expressed as option A PO2 upon under root O, option B PO upon under root PO2, option C 2PO upon PO2, option D PO2 upon 2PO. So we have this reaction 1/2 O2 is O. Equilibrium constant, how it is given by Kp is I Pi minimum. So for this reaction we have two species. So mu O is nothing but 1 and mu O2 is nothing but 1/2. So what will be the Kp? Kp is product of Pi into Dy, so it will be P O mu O into PO2 to the power, and mu is 1 and mu2 is 1/2. Sorry, this mu2 is minus 1/2 because this is the reactant, and if it will go right inside it will become minus. Here also minus 1/2. So it will be nothing but Pu upon under root PO2. So option B will be the correct. Now we will see one problem. Derive the following relation between the equilibrium constant and the heat of reaction. D log Kp upon dt equal to delta Hr upon R T square. One thing is that we have not defined what is heat of reaction. So heat of reaction delta Hr is nothing but enthalpy of product minus enthalpy of reactant. So it can be given by sigma mu I Hi, where Hi is the enthalpy of species I and mu I is the stoichiometric coefficient. So If you see this expression carefully, it is taking the derivative of log of equilibrium constant. This is equilibrium constant. So first we will write equilibrium constant in its logarithmic form. So we know that Kp equal to pi I Pi mu I equal to e to the power minus delta G P equal to 1 upon R bar T. We'll take these two terms. If we take the log on both sides, then log Kp equal to minus delta G P equal to 1 upon R bar T. And what was the value of this delta G equal to 1? We have seen this relation. This one. Delta G equal to 1 equal to sigma I mu I Gi P Pi equal to 1. We'll substitute this back again. So we will get log Kp equal to minus sigma mu I Gi P equal to Pi equal to 1 upon R bar T. Now we will take the differentiation of this with respect to temperature. So if we take the differentiation with respect to temperature, first we will take differentiation of this term, then this term. So if we take the differentiation of this term, it will become sigma mu I Gi Pi equal to 1 upon R bar T square. Differentiation of 1 by T will become minus 1 by T square, and minus minus will become plus. For the second term, it will become minus R bar T, minus 1 by R bar T, and differentiation of this term. I have just skipped one term, but it will be differentiation of this term, dy dt sigma mu I Gi Pi equal to 1. So if we take its differentiation, so the sigma differentiation can go inside. So here I'm writing it here. This differentiation can go inside, and it can become sigma d by dt mu I Gi Pi equal to 1. And we already know that mu I is constant, so it will come out. So it will become minus 1 by R bar T sigma mu I dgi Pi equal to 1 upon dt. Now we will see the relations. This TDF relation, TDF equal to dhi minus V bar I dpi. How do we got this? There was one relation I mentioned before. This relation is del Q reversible equal to dH minus V bar dp. And if we write it for one species, then it will come del Q reversible I equal to dhi minus V bar I dpi. And del Q reversible is nothing but TdS. We have written as TdS because this ds reversible is 0 for equilibrium. So TdSi we got TdSi equal to dhi minus V bar I dpi. and there was one relation which we already have, d dhi equal to dhi minus t dsi minus si dt. This is from the definition of G. This is from definition of GI. So here if you see this TDS, from this we can find dhi minus tdsi equal to vi bar dpi. So this term became this one, vi bar dpi, and this is si dt. Now if we make prefer pi equal to constant and equal to 1, so dgi pi equal to 1, this term will become 0. We will get minus si dt. So its derivative will be dgi pi equal to 1 upon dt equal to minus si. We will substitute this in equation A. This term we will substitute, so we will get d log kp upon dt, write properly. So what we got it, d log, I have skipped their steps, so I am writing it again, upon dt equal to minus 1 by r bar t square sigma mu I gi equal to 1 minus 1 by r bar t sigma mu I minus multiply by minus si. So this minus will come out and it will come plus here, and we can take 1 by r bar t square as constant. So we will get sigma I mu I gi pi equal to 1 minus t sigma mu I si. Sorry, this is plus. This one. This t we will take it inside because t is constant for each species. So it will be 1 by r by t square sigma mu I gi pi equal to 1 I plus sigma mu I t si I. Now we will take this summation together. So if we take it together, then it will be 1 by r bar t square sigma I mu I gi pi equal to 1 plus mu I t si. Here we can take mu I as common, For taking mu I is common, we'll get 1 by r bar t square sigma mu I gi pi equal to 1 plus tsi. And we know that gi pi equal to 1 plus tsi equal to hi. We are getting at a constant pressure this term. So we will substitute it hi here. So we will get d log Kp upon dt equal to 1 by r bar t square sigma mu I hi. Now we have seen the definition of heat of reaction, which was nothing but enthalpy of product minus enthalpy of reactants, which is equal to sigma mu I hi. We substituted here as delta hr and we'll get d log Kp upon dt equal to 1 by r bar t square delta hr. This was what we have to prove, so it is proven. Now, whatever relation we have used, only one thing we have not proved, which is the equation for entropy. This equation, entropy of a species of the gas, SI equal to integration T reference to T Cpi dt upon T minus R bar log Pi upon T reference plus SI reference. So we will prove this relation, entropy for species. So we are calculating it for species I per mole of the mixture. So for the equilibrium, flow, T dsi equal to del Q reversible. We know this from the definition of entropy, and this del Q reversal is nothing but dhi minus vi bar dpi. This all properties are for the 1 mole of mixture. That's why there is this v bar. This bar is for molar volume. So we'll get dsi equal to dhi upon T minus vi upon T dpi. Now we'll use two relations. One is that dhi is equal to Cpi dt, where Cpi is function of temperature for thermally reacting gas. For one species alone, it will always be a thermally perfect gas, and there will be no effect of any other gas. So this relation, and one is that Pi pi bar equal to r bar t. This r bar is universal gas constant. Everywhere where I use r bar, this is for molar quantity. So this r bar is universal gas constant. Bi is molar volume. So Bi upon T we will get equal to Bi bar upon T. It is nothing but R bar upon Pi. So when we put all this value in this equation B, we will get dSi equal to Cpi dt upon T plus minus R bar dPi upon Pi. We will integrate this quantity from one reference value to Si. Temperature also it will be from T reference to T, and pressure also this R bar I am taking out because it is constant. Cpi is not constant, it is function of temperature, so it will remain stable inside this integral. It will be Pi reference not Pi reference, P reference to Pi. So if we integrate it, we will get Si minus Si reference equal to, this term will remain same because we don't know how this Cp is depending on temperature. And this term it will give log Pi upon P reference. This Si also we can take on the right hand side, Si reference also right hand side. So ultimately we will get the value of Si equal to integral T reference to T Cpi dt upon T minus R bar log Pi upon P reference plus Si reference. This is the value of, this is the entropy which we have used before. So today we have solved some problems mainly related to equilibrium constant, equilibrium flow, and chemical non-equilibrium, perfect gas relations. We can solve more relation related to perfect gas relation from some any fluid dynamics book, and this chapter general reference you can find in this book. Hypersonic and high temperature gas dynamics. High temperature gas dynamics. By J.D. Anderson. you can refer to this book and you can try following the problems related to this chemical molecule. And generally this equilibrium constant is used for finding the pressure and their stoichiometric coefficient. Sorry, uh, for finding the pressure and the number of particles present in the gas. So generally, let's say there are some reactions. Let's say there are two reactions. So we can use this Kp. So we can find the pressure ratio of the species in terms of this Kp. So we'll get some equation from there, and we can also find the number of we can also find the ratio of number of particles in terms of this pressure ratio, this pressure value, partial pressure value. So using those relations, we can find the number of particles present for each species. And for doing the calculation of equilibrium flow, generally we should know the chemical reaction. So generally, if we don't know the chemical reaction, we take all the species which might be present in the flow. So after doing the possible chemical reaction also, and after doing the calculation, whatever the species you find in the low quantity, you can neglect that and chemical reaction related to that species. Like this, you generally find the what are the chemical reaction happening in the hypersonic flow and what are the species. So today I will end my class till here only. If you have any doubt, you can ask in the discussion forum related to it. Okay. Thank you.